Working on lesson 1.7, scale drawings on page 43. Our learning goal for the day is to be able to explore scale drawings. Now here are some drawings of a school bus, a quarter, and subway lines around Boston, Massachusetts. The first three drawings are scale drawings of these objects. So these following are scaled drawings. Now if you look at the next three, 4, 5, and 6, notice that those are not scale drawings of these objects. Discuss with your partner what a scale drawing is. So what I'm going to do is write down my scaled drawings to the left and draw things that are not scaled on the right. So whenever we think of scaled drawings, there's always some real world aspect to it. There's something out here in the real world that exists that you are drawing a model of that object for whatever particular reason. Now, if your parents work in construction, a lot of times before they build a house, they have to give plans. Plans are literally just scale drawings of what they plan to build. Now, it is important whenever drawing scale drawings that you have some type of accuracy. Some way you are telling the reader how big or how small your real world object is going to be that you plan to build, and so forth. Now, notice that when you're dealing with non-scaled items like 4, 5, and 6, they're a little less accurate. They're more used to represent just things and not exactly anything in particular that has importance to its size. A lot of times they could be something like doodles. Although they represent real world things, we really don't care about their sizes. They're usually just done for fun, like 4 and 5. Sometimes, like in 6, there are non-scale drawings that are done for convenience purposes. As you can see, these lines are probably used for travel. They're a little easier to understand where to go in comparison to our real world, more accurate descriptions of how the subways flow through Boston. So now that we've talked a little bit about scale drawings and know that they tend to be drawings of real world things with accurate measurements, let's go ahead and flip the page and look at a specific example. Now, if we flip the page, you'll notice that I'm going to give you a scale drawing of a basketball court. Now, the drawing does not have any measurements labeled, but it does say that 1 centimeter represents 2 meters. Now, this basketball court that you can see in my dot cam represents the actual measurements that have been scaled down from some real world basketball court. Now, of course, I won't be able to find a paper big enough to draw an accurate representation of actual basketball court. So that's why we sometimes scale things down. Now, notice that when they scale things down, they said that 1 centimeter in this drawing represents 2 meters out there in the real world. Now, I don't know actually what basketball court this is drawn after, but I'm going to take it as true that there exists some real world basketball court out there where the measurements are found from one another. All right, so let's go ahead and look at question 1. Measure the distances on the scale drawing that are labeled A through D to the nearest tenth of a centimeter. Record your results on the first row of the table. Now, our table is in question 3, but we're going to go ahead and measure all those lengths. I can see that length of A is going to be the length of the court, B is going to be the width of the court, C is going to be the hoop to hoop, and D is going to be the 3 points in the sideline. So let's go ahead and start with measuring on our scale drawing the length of the court. Now, when I look at the court here, I can see here that the length of the court goes from this dotted line to this dotted line. Now, they are asking us to measure it in centimeters. Whenever you get a ruler, it's usually going to be measured in centimeters or in inches. Make sure you're using the correct side. Since they told us to use centimeters, we're going to go ahead and use the centimeter. Now, in order to measure, I'm going to place my 0 at the beginning of whatever I'm trying to measure, and I'm going to go ahead and measure to the very end. Now, I can see that it's very near 14, close enough to say that the length of the court, the measure of A, is 14. Now, let's go ahead and look at B, the width of the court. Now, if I look at the width of the court, I notice that it is B, which could be found right over here. Using my centimeter sign and reminding myself not to get confused or measure in inches, I'm going to go ahead and place my 0 right at the dotted line and see where it ends up at, which is around 7.5 centimeters. Now let's go ahead and measure hoop to hoop. Now the hoop to hoop is going to be C, which can be found right there in the middle. I noticed that the dotted line starts right at one hoop and ends at the other hoop. Now this one's a little challenging, but I see it could be roughly about 12.3. So I'm going to go ahead and write that measurement down as 12.3. Now, last but not least, let's go ahead and do point D, which is the 3-point line to the sideline. Now I can see that's going to be a little smaller than all my other measurements, but in centimeters it looks to be perfectly about 0.5, about half a centimeter. So now that we have finished measuring the measurements in our scale drawing of the basketball court, let's go ahead and concentrate on our activity. Now we finished problem 1 by recording those measurements. Let's go ahead and move to question 2. The statement 1 centimeter represents 2 meters is a scale of the drawing. It could also be expressed as 1 centimeter to 2 meters or 1 centimeter for every 2 meters. What do you think the scale tells us? Now, of course, take this time to discuss with your partners. Now, I'm going to go ahead and just jump in. So if you guys remember, this basketball court, this drawing of the basketball court represents some type of scale drawing. Now, of course, I'm going to do this as much as possible to get the point across. Now, that scale drawing is a representative of some huge object out there in the real world. Now, of course, we can't make a perfect drawing with exact measurements because we wouldn't be able to find paper big enough to measure some things as big as a basketball court. So, what does this tell us? This tells us that if I have 1 centimeter for every 2 meters, that 1 centimeter in our scale drawing is going to represent 2 actual meters in our real world drawing. So for this instance of the basketball court, if I were to measure 1 centimeter on the court, and if I go to the real world representation, it would be 2 meters in that instance. Now, one way we could use this to help us for future problems is by putting the exact same information in the form of a table. So if I have a table, what I could do is place all my measurements to the left that are scaled drawings. We know that those are going to be done in centimeters. And then to the right, what we could do is place our real world. And we know that those are going to be meters. Now, we know that for every 1 meter in our scale drawing, it's going to give us 2 meters out in the real world. I noticed that that table is just another way to represent exactly what I explained as a drawing. All right, so how long could each measurement from the first question be on an actual basketball court? Explain your reasoning. So what they're asking us is, okay, we just took a bunch of measurements of this scale drawing. What would be the measurements on the actual court, the real world court in this instance? Now, looking at our table, it makes it a little bit easier to see what we can mathematically do to our values of our scale drawing to figure out what the values would be in the real world. Now, looking at this instance, I can see that, okay, there might be a scaled factor. A scaled factor will help us go from our scale drawing measurements to the corresponding sides of the real world. Now, looking at that, 1, what can I multiply that 1 to equal to? So I notice that all I would have to do is multiply each value by 2 to figure out how many meters it will be in the real world. So if my scale drawing in the length of the court is 14 centimeters, to be able to find the actual length, all I would have to do is multiply by 2. 14 times 2 is 28. Now keep in mind we're going from centimeters to meters, so that means we would have 28 meters in the real world. If we were finding the width of the court, we would do the same thing and multiply it by 2. 7.5 times 2 is going to be 15. Don't forget that we're going from centimeters to meters. Now, 12.3 times 2 would be 24.6 meters. Last but not least, the 3-point line to the sideline, multiplying it by 2 would then equal 1 meter. So we could use this to figure out what the lengths would be in the real world. Now, if I want to figure something out, I don't have to go to the real world and measure the actual, I could actually go to the picture. Now let's go ahead and look at question 4. On the actual basketball court, the bench area is typically 9 meters long. Without measuring, determine how long the bench area would be on the scale drawn. So let's go ahead and draw the exact same table that we did above. Now remember that on the left we have our scaled drawings, our scaled measurements given in centimeters, and on the right we have our real world measurements, which would be in meters. Now they are telling me that the actual basketball court, the actual bench is 9 meters long. So that means that my 9 would be on the side of the real world. Now without measuring our scale drawing on the basketball court, let's go ahead and find out what would the scale measurement be. Now, remember that our scale factor has not changed. In order to go from our scaled to our real world, we know that we have to multiply those values by 2. Now, in order to work backwards and figure out how to go from real world to scale, we're going to do the opposite. So instead of multiplying, we're going to go ahead and divide by 2. Now, 9 divided by 2 is just 9 divided by 2, but what you also do is remember, whenever you're dividing, you can technically multiply by the reciprocal. So if we multiply by the reciprocal, we can multiply by 1/2. 9 times 1/2 will give us the exact same value of 9 divided by 2. Now let's go ahead and change this to a decimal. 9 divided by 2 would be 4.5. Now let's go ahead in our actual drawing to see if this agrees. Because according to this, if I have in the real world a 9 meter bench, and my drawing should have a 4.5 scale in terms of my drawing. So let's go ahead and check to see if we did it correctly. Now if you notice in our drawing, our benches are drawn right here at the bottom. Let's go ahead and measure to see if we actually get the scale drawing of 4.5 centimeters. Here's my centimeter side. I'm going to go to the beginning of the bench to the end of the bench, and you can see here that it's exactly at 4.5. So we were correct. Now that we've finished activity 7.2, let's turn the page and see what the next activity is. So here are some scale drawings of the world's tallest structures. We have the Great Pyramid, Eiffel Tower, Willis Tower, CN Tower, and Burj Khalifa. Question 1 is asking us how tall is the actual Willis Tower, and about how tall is the actual Great Pyramid. Now, all we have to be able to do so is this little scale drawing. Now, I notice that in my drawing, this distance represents 100 meters. So I'm going to go ahead and use that fact to be able to find the actual distance of the Great Pyramid and Willis Tower using this scaled drawing. Now I'm going to go over to my dot cam to show you one way, and then of course we're going to figure out another way towards the end. So my goal here is to be able to find the distance, the actual distance of the Great Pyramid and the Willis Tower. Now if I look at the scale, I notice that the distance covered from here to here represents 100 meters because it has 0 to 100. So what I could do is take that little scale and figure out how many of they are in my scale drawing. So if I look at this one, I notice that the distance from here to roughly about there is 100 meters. Notice that you have a little bit more from here to here. Now, of course, I'm not going to be able to be exact, but I'm going to go ahead and say that that's roughly about 20 meters. So if I know this distance here from the beginning of my scale was 100, and this was about 20, I noticed that the Great Pyramid was roughly about 120 meters tall. Now let's go ahead and look at Willis Tower. I'm going to start from the bottom of my scale and say, okay, from the distance from here to the Willis Tower here is roughly about 100. Now if I were to put that same scale on top, I notice that that would be another 100 there. I notice that there would be another 100 here. And then finally, looking at this from the top, would be about another 100. Now again, this isn't going to be the most accurate, but you could use your scale to get an idea about how actually tall it is. Let's go ahead and figure out how tall in total. So this is 100, 200, 300, 400. It's roughly about 400 meters tall. Now, how much taller is the Burj Khalifa from the Eiffel Tower? Explain or show your reasoning. So in order to do that, we're going to go ahead and find the tallness of Burj Khalifa and Eiffel Tower and find the difference. Let's start with the Burj Khalifa. Now, if I use the scale here, that's going to be 100. Next one's going to also be 100. One more is also going to be 100. Another 100. Another 100. One more 100. And then finally, I can see that there's one more 100 left. So in total, there was 1, 2, 3, 4, 5, 6, 7 of those scales, which is going to represent about 700 meters. Let's go ahead and look at the Eiffel Tower. From the bottom of the Eiffel Tower to roughly right about there is going to be 100 meters. The next one up is going to be another 100 meters, and then about half, which would then represent 50. So we can see here that the Eiffel Tower is about 250 meters tall. Now, how much taller is the Burj Khalifa in comparison to the Eiffel Tower? Well, let's take 700 and subtract it from our Eiffel Tower height, and let's figure out how much taller it would be. 700 minus 250, 0 minus 0 is 0. I can't take 5 from 0, so I'm going to go ahead and borrow. 10 minus 5 is 5, and then 6 minus 2 would be 4. So how much taller is the Burj Khalifa? It's about 450 meters taller. Question 3 states, measure the line segment that shows the scale to the nearest tenth of a centimeter. Express the scale drawing using numbers or words. So what I can notice here is that this little line here represents 100 meters. Now what I could do is actually measure that little line in centimeters to see how many centimeters it would take to get 100 meters in the real world. I'm going to go ahead and line it up from the bottom, from the top, and see where it ends up. And it roughly ends up at around 0.7. So the distance right about here would be about 0.7 centimeters. So that means that for every 0.7 centimeters is the same for every 100 meters in the real world. Now again, you could use this fact in knowing that it's 0.7 centimeters for every 100 meters to also measure the Burj Khalifa in centimeters in our drawing, and then do the math to figure out how many the distance would be in meters. All right, so if we flip to the last page, so page 46, we have our summary. Now in our summary states, scale drawings are two-dimensional representations of actual objects or places. Floor plans and maps are some examples of scaled drawings. On a scaled drawing, every part corresponds to something in the actual object. Lengths on the drawing are enlarged or reduced by the same scale factor. A scale tells us how actual measurements are represented on the drawing. For example, if a map has a scale of 1 inch to 5 miles, well then 1/2 inch line segment on the map will represent the actual distance of 2.5. Sometimes the scale is shown as a segment on the drawing itself. For example, here's a scale drawing of the top part of a stop sign with a line segment that represents 25 centimeters of actual length. The width of the octagon is about 3 times the length of the segment, so the actual width of the sign is about 3 times 25 or 75 centimeters long. Because a scale drawing is two-dimensional, some aspects of three-dimensional objects are not represented. For example, this scale drawing does not show the thickness of the stop sign. A scale drawing may not show every detail of the actual object. However, the features that are shown correspond to the actual object and follow the specified scale.